this ALUCAST 2020 virtual conference, the theme of which is aluminum casting technology for the 20s. We have a host of interesting speakers and presenters from India and abroad, and I can assure you that you will have an extremely interesting 2 days ahead of you. The conference itself has attracted tremendous support from a host of sponsors. And as we set the ball rolling for the day, it is my estimate that almost 300 people are taking part in the proceedings, some of whom are sitting in the front of large screens in workplaces. Without further ado, let me introduce the principal speaker for the morning to permit him to give his opening remarks. He is Mr. T. Parabrahman, a trustee of ALUCAST based out of Bengaluru. Mr. Parabrahman is a graduate in mechanical engineering from Bangalore University, and he started his career way back in 1973 at Bharat Fritz Warner, an Indo-German machine tool industry in Bangalore, and then joined Mysore Kirloskar Limited in 1990. Mr. Parabrahman was a member of the core team responsible for the formation and setting up of Kirloskar Toyota Textile Machinery Limited, or KTTM as it is known, the first joint venture between the Toyota and Kirloskar groups at Jigani, Bangalore. He was associated with the company from its very inception in 1995 as its vice president and was appointed as the CEO and managing director in 2008. He retired from the company in July 2012. KTTM, under his leadership, grew into one of the unique companies of India, with a distinction of being the only company to manufacture high technology spinning machines for the textile industry and high volume auto components, including one of the largest aluminum die casting facilities in South India, in the same campus by the very same people. The company has received many awards and accolades for the excellence in quality, productivity, and innovative practices. Mr. Parabrahman's policy of touch the heart, people first, had ensured that all the employees had a great pride of being a part of the organization. Mr. Parabrahman was the chairman of CII Karnataka, the vice chairman for affirmative action and CSR of CII Southern Region. He has been associated with the Government of India funded research and development of precision machine tools and advanced textile machineries at IIT Madras and CMTI. Mr. Parabrahman is currently on the board of BFW as an independent director. He is a trustee at ALUCAST, the Aluminum Casters Association. He is a vice president of the National Association of Blind, a member of CII's Karnataka State Council, and he also advises. And gentlemen, I give to you Mr. T. Parabrahman. Sir, the floor is yours.
Thank you, Kabraji. Thank you very much for the introduction. Very good morning on behalf of the President of ALUCAST, Mr. Prasan Firodia, my fellow trustees of the association, all our zonal chairmen, our secretariat led by Dynamic Secretary Mr. Kabraji. It is my pleasure and privilege to welcome you all to this virtual conference by ALUCAST. As mentioned, this is the first of the kind resulting out of our experience and response to the multiple webinars conducted over the past 6 months. This conference has elicited a tremendous response with nearly 150 delegates or more from all over the country to listen and interact over the next 2 days with a galaxy of domain experts covering a wide array of technologies relevant to the die-casting industry. We would also have the opportunity to see some of the unique product presentation to help us brainstorm the way forward. The pandemic of COVID-19 has impacted every aspect of our lives. In spite of total lack of awareness during the initial period of the pandemic, the world has united to fight for survival, and the battle is being fought with the use of information technology, innovative medical practices, and most important, by the wonderful set of human beings whom we call the COVID warriors. Corona has taught us to respect environment and made the world think differently, to innovate and depend on each other. The world saluted India as it rose to challenge of mass manufacturing of masks, PPE kits, ventilators, and other medical equipment uh, and drugs, not only to meet our own mega demand but also for the world. This great effort has resulted in opening the doors to many opportunities for us to become manufacturers for the world. The Prime Minister's call of Atmanirbhar Bharat, the produce in India for the world, should not remain as a slogan, but a way forward for all of us in the industry. Aluminum casting industry is no exception, and we see a new opportunity in every aspect of the die casting process. The surging demand from the auto, the electrical, the white goods, aerospace, and defense industries is a clear indication that the pendulum, which has swung towards the gloom and depression, has now started swinging back with a great momentum towards a greater global demand cycle. We at ALUCAST had planned our mega international show, ALUCAST 2020, in December at Chennai, along with our exhibition partner Nuremberg Messe. We had to call it off, but looking at the opportunities ahead of us, it was felt that it would be very appropriate to have this virtual conference with the theme Aluminum Casting Technologies for the 20s. I'm sure there will be many takeaways in this form of new ideas, learnings at the end of 2 days of this event. I'm thankful to all our speakers, sponsors, and other who made this event happen. The one aspect we shall all miss is the networking among the participants in a physical event, but we should soon find a way to do that again. Finally, I wish you all the very best, and with your approval, dedicate this event to these COVID warriors of the world. Thank you and have a wonderful event.
Thanks, Mr. Parabrahman, for all those encouraging words. And I think we are moving absolutely on time. So I'm Secretary of our Delhi Center, uh, Mr. Anurag Luthra, to take the stage and introduce the United States of America. Good morning to you, Steve. Steve Midson. Good to see you. It would have been great if we had met in person again, but virtual it has to be. Take it away, Mr. Luthra.
Yeah, good morning, everyone. This is Anurag Luthra from the Delhi chapter of ALUCAST. We will be beginning our first session now. And I have the privilege to introduce the first speaker. That's Mr. Stephen Midson, President of the Midson Group. Popularly known as Steve. He has been associated with us for quite long now. He is the president of Midson Group, Denver, USA, and is also empaneled with NADCA. He has authored books on die casting dies with special emphasis on improving die life. He has conducted 2 and 3 day training programs at different centers, and we had the privilege of having him at Pune, Delhi, Bangalore, Ludhiana in the years 2018 and 2019. On behalf of ALUCAST, Dr. Midson is associated with research groups in the US and China, where he is also a consultant. Well, he will be giving a paper today. The paper reports on a 5-year plant trial where an entire die casting die was covered with a physical vapor deposited. We can call it as PVD. It's a ALCRN coating. The results have shown that the coating entire die allowed a significant reduction in the amount of lubricant to be applied to the die. This has resulted in a number of documented benefits, including a reduction in soldering and erosion problems, an improvement in cycle time, and reduction in manufacturing costs. Expensive die repairs can be postponed, and most importantly, a significant extension of the die life was attained. So I hand over now the session to Mr. Steve Midson. We'll be having this for about 30 to 35 minutes and followed by questions in the last 5 minutes. So welcome on board, Steve. You can start the session.
Okay, thank you very much. Can you guys hear me? Can you hear me?
Yes.
Okay, great.
Loud
Let me share my screen, and hopefully you can see my slides too. Okay, can you see that?
You can see a white screen.
Uh-oh. That's not good. Can't see the slide?
We saw you and then you vanished.
But can you see the slides?
No, can't see the slides. No.
All right, hold on. I'm going to stop sharing and try again. Let me try that. How about that?
Yep.
Yes.
Okay. All right. So good morning to everyone, or good evening here in the States. As the chairman said, I'm going to be talking about extending die life through surface treatments. So obviously, tooling is a major cost for all die casters, but there's a great financial reward that can be obtained if we can actually get an increase in die life. So over the years, all sorts of new die materials, new heat treatments, and more recently, coatings have been explored to reduce the incidence of premature die failures and to increase die life. So the one I'm going to be talking about today, as we just heard, is physical vapor deposition, or PVD. And these coatings are one such technology, and they're well known to reduce soldering and erosion in die casting, but the effect on heat checking is less clear, and that's kind of what I'm going to be talking about today. So this slide kind of summarizes surface engineering technologies that can be used for die casting and other type of industries, and we're talking about coating the dies. And so if we call the whole thing surface engineering, I've split it down by 3 groups: surface treatment, hard coatings, and weld overlays. And so surface treatments are the kind of treatments that we're kind of used to in die casting: nitriding, ferritic nitrocarburizing, where we are diffusing either nitrogen or carbon plus nitrogen into the surface of our dies, normally about 100 microns or so, and we get hard layers on the surface of our die. So those are pretty commonly used in die casting. Hard coatings are more newer over the last 20 years or so, and basically consists of PVD, physical vapor deposition, and CVD, chemical vapor deposition. CVD is not used a lot in coating dyes because normally the substrate temperature has to be raised to too high a temperature and will soften the dye. So PVD is the process that's normally used. Then the third one is weld overlays. Weld overlays, at least in my experience, are not commonly used in die casting, but have been used in the forging industry, where they also use H13 steel dies. And so we're not going to really be talking about that today. So the focus today is going to be on hard coatings, mostly PVD type coatings. So in the presentation, as the chairman said, I'm going to be providing some results of a 5-year plant trial that's been going on in the US. And the goal of the trial was to examine the impact of applying a PVD coating to an entire die. So any part of the die that was contacted by the liquid aluminum, we put a PVD coating on. So I'm not talking about just coating small cores or small inserts, coating essentially the whole die. And so the goal was, could we apply PVD coatings and reduce the amount of conventional spray lubricant applied to the die? Basically, can a PVD coated die be run lubricant free with no sprayed lubricant at all? As it will show a little bit later in my presentation, we didn't quite achieve that, but what we did see by reducing the amount of lubricant due to the PVD coating is that we got a whole range of other benefits that I'll describe later in the presentation. So before I go on to talk about the plant trial itself, let me discuss mechanisms that can cause failure of die components, basically heat checking, soldering, and erosion. So let's talk about heat checking first. And so I think as die casters, we're all familiar with heat checking, the formation of fine cracks on the surface of the die. And this occurs due to thermal fatigue, which is coming from the heating and the cooling of the die surface every time we make a casting. And so this figure is taken from a paper by Jack Wallace and his co-workers from a NADCA Congress paper back from 1999. And the vertical axis shows the surface die temperature in degrees centigrade, and on the x-axis we're looking at cycle time or time in seconds, and we're looking at about 1.5 cycles here. And so we're looking at about 10 thousandths back from the surface of the die face, so that's about 1/4 millimeter. Looking at 60 thousandths of an inch back, that's about 1.5 millimeters. And then 1/2 inch back, that's about 12 millimeters or so. So what we see is as the liquid metal is injected into the cavity, the surface of the die heats very, very quickly and then starts to cool. And then as the cavity is opened, it starts to cool even faster. And then obviously as we spray the surface, then it cools really, really quickly. Once the spray stopped, then the surface die temperature has recovered. But what we see is that 1.5 millimeters back, we don't see quite as hot at as the surface when the metal is injected, and we don't see quite as cold as the surface when we're spraying. And 12 millimeters back, we still see an up and down, but not quite as much. What this means is that we get this thermal fatigue cycle every time we make a casting. When we inject the liquid metal, the die surface is in compression. When we spray, the die surface is in tension. So this tension, compression, tension, compression gives us a fatigue cycle, and this thermal fatigue leads to heat checking or cracks on the die surface. Then if we go on and talk about soldering. Soldering, again, most die casters, I'm sure, are very, very familiar with soldering. This is when the molten metal sticks or solders to the die surface and produces a scab on the surface of the casting once we eject the casting, and then a small amount of the solidified aluminum remains on the die after the casting is ejected. There's been several papers over the last 20 years or so providing the mechanism for soldering. Back in 2000, Shankar and Pelian gave a 6-step mechanism for soldering of the aluminum to the steel. They said initially the molten aluminum chemically attacks the die steel, mostly at the grain boundaries. And then we get formation of an intermetallic phase between the molten aluminum and the steel die. So the aluminum forms a compound or an intermetallic phase with the iron from the steel. And this phase acts as a glue so that the solidified casting sticks and solders to the steel die and makes it difficult to eject. A couple of years later, another couple of researchers, Vishwanathan and Han, came along, and they said that they identified a minimum die temperature below which soldering will occur. So below the temperature, no soldering. Above the temperature, we get soldering. And again, that's kind of familiar to most practical die casters. However, what's kind of recently, just in the last couple of years or so, a couple of researchers in the US, Monroe and Sanders, have kind of come along and questioned these mechanisms, whether it really is aluminum intermetallic phases as causing the soldering. And so at the moment, at least, the mechanism for soldering is still a little bit up in the air. And then for erosion, erosion is the gradual removal of the cavity die surface due to either mechanical action or to chemical dissolution. This is not the greatest photograph, but it kind of shows a little bit of erosion here, where part of the steel die has been removed by the action of the molten aluminum moving over it. And so there's basically 3 mechanisms for erosion. We have liquid impingement erosion. This is when the liquid aluminum, for example, is a very high velocity around the gate, or maybe impinging directly on a core very close to the gate. And basically the steel die is dissolved by the liquid aluminum. Then we can also get solid erosion. This is caused by the impact of solid particles during die filling, hitting on the die surface. Where do the solid particles come from? Obviously, silicon particles pre-solidified in the aluminum alloy. Oxides can be very hard, very abrasive, and they can cause quite serious erosion. And then other impurities, solid impurities in the aluminum alloy. Then a third mechanism for erosion is cavitation. Cavitation is a special type of erosion. This is when we get the formation of small bubbles as the liquid metal is filling the cavity, and then the bubbles collapse at very high velocity and very high pressures against the surface of the die and can cause quite a large amount of damage. And often we see this more in zinc die casting dies, not because it's more important in zinc, but some of the other mechanisms that we've talked about, such as heat checking and soldering, are less important in zinc die casting, and therefore we see the effect of cavitation because often the zinc die casting dies last a long time. So let me go on and talk about the plant trial. As I said at the beginning, it was a 5-year plant trial that was started in 2016. And so initially I'm going to talk about the early stages of the plant trial, and then I'll give some information, more recent results that we're kind of seeing from the plant trial. So the plant trial was started in 2016 and was based on research results obtained at the Colorado School of Mines. The research objective, as I've talked about before, is that if we pick an appropriate PVD coating and we apply it to all surfaces of a die casting die, can we totally eliminate the need for conventionally sprayed lubricants? Early on in the project, there was a lot of laboratory research performed at the university, at the Colorado School of Mines. and that showed that an aluminum chromium nitride coating was the best candidate. And so that was picked for the plant trial. So this is the casting that was chosen for the plant trial. It's a balance shaft housing, and it's used in the motor of an outboard motor for marine applications. It's about 150 millimeters by 150 millimeters in size, weighs about 0.8 kilograms. It's produced in a single cavity die using a 700-ton die casting machine. And so these are some models showing the moving side and the fixed side of the die. And as I said before, any part of the die that is contacted by molten aluminum was covered with the aluminum chromium nitride. So on the moving side, that include the runner block, the runners, the cavity, the ejector pins, the overflows, the vents, and the vent block. And then it's exactly the same on the fixed side, the runners, the cavity, any core pins, and we don't show the vent block here, but that was also covered. What was nice about this die is that the caster that produced it had previous experience. They've been producing this casting for many years, and so they had experience with an old uncoated version of the die. And what they saw is that die had a die life of about 97,000 shots before it had to be replaced. And for the uncoated die, it was necessary to spray lubricant for 12 seconds. So here are the results of the plant trial. So on day one for the coated die, initially we went from 12 seconds with the uncoated die to 2 seconds with the coated die. That's an 83% reduction in spray, and 70 castings were produced with no evidence of sticking. So then they went down to 1 second of spray, which is about the minimum amount of spray that they could run with their equipment. That's a 92% reduction in spray from the 12-second use previously, and they produced 30 castings with no evidence of sticking. So then they went to no spray, and they turned the spray off, and the first casting stuck. And not only did it stuck, but it actually bent on ejection, as you can see here from the photograph. And so it looks like heavy sections close to the gate soldered and stuck. And then during removal of the stuck castings, some core pins were bent, so the die had to be taken off the machine, disassembled. Luckily, we had spare coated core pins that we could put back in, reassemble the die, put it back on the machine, and run it the next day. And so on day two, the die was replaced, and 92 more castings were produced with this 1 second lube spray. That's a 92% reduction in spray. And again, no evidence of sticking. So we didn't quite get to lube-free, but pretty close. And what we saw were some other benefits that we observed from using the low level of spray. And the first one was cycle time improvement. We were able to improve the cycle rate by about 12%, so cast 12% faster with the PVD coated die. Why? Because we weren't spraying as long. We used to spray 12 seconds, now we're spraying 1 to 2 seconds, so we can reduce the spray time, so the number of castings per hour is higher, and therefore production costs are lower. But what was kind of interesting is this figure at the top here is comparing cycle times for 11,652 shots produced in the coated die versus 27,733 shots produced in an older uncoated die. And so if you look at the median rate, we can see this is the 11.82, 12% improvement in the median casting rate. But if we look at slightly slower castings, the third quartile, that was faster by 18%. And what we think is happening is that the PVD coating is producing a more consistent cycle rate because we don't have to stop, or the caster didn't have to stop and clean the die so often. They didn't have to go in there and clean solder off the die quite as often with the PVD coated die, so they could actually go 18% faster. So a big improvement in cycle rate, which obviously again comes down to cost. So as I said, that was done back in 2016, 2017. The plant trial is continuing. And so now here's some more recent data from 2019 and 2020. And so as I said, the information before came from 2016, 2017, but because the caster is only producing somewhere between 20 to 25,000 balance shaft housings per year, they're still running the die. So the plant trial is essentially still continuing. And the PVD coated die recently produced more than 100,000 castings in the same die. And as I said earlier, as a reference, the older uncoated die was retired after 97,000 castings had been produced. So we're already doing better than the old uncoated die. And so here's a photograph of the PVD coated die after 100,000 or more than 100,000 castings have been produced in it. At the bottom, you can see the ejector side, at the top, the fixed side. And certainly looking at this view, it seems to be still in excellent condition, even after the production of 100,000 shots. I should say that this PVD coated die has required one welding repair operation that occurred after around 75,000 shots. However, the old uncoated version of the die required its first weld repair around 37,000 shots. And had a total of 3 weld repairs by the time it got to 75,000 shots. So only one weld repair for the PVD coated die, 3 weld repairs for the uncoated die. However, the picture I showed was a little misleading. The die isn't quite in as good condition as it looks when you kind of look at it from afar. When you look a bit closer, there is some minor heat checking and other damage going on. And so the photographs now on the right are kind of close-ups, again on the top from the ejector side of the die, lower from the fixed side of the die. And the areas that we have circled in red or with red arrows are kind of showing some of the areas. So if you look at the ejector side, there is some minor heat checking on the shaft region, on the circular regions, and around the ejector pin area. And then on the fixed side, there's a little bit of heat checking damage here. And then between the shaft regions, of the die. But again, this die has run 100,000 shots. And again, as a reminder, the old uncoated die had to be retired and replaced after only 97,000 shots. So the PVD coated die does appear to be in excellent condition after the production of 100,000 castings, and is likely to run considerably more shots before it is finally retired. This is showing the pictures of the castings produced in the die after 100,000 shots. And because the die looks so good, it's not surprising that the castings also look very good, but they do. And again, here are pictures of a casting produced in the die after 100,000 castings had been produced. So this kind of begs the question, is it the PVD coating itself? Or is it the reduction in spray that's allowing for this significant improvement in die life? And I think the answer is we don't really know yet. I'll give you my opinion. My opinion is that I think it's unlikely that it's a PVD coating itself. PVD coatings are typically quite thin, normally somewhere between 2 and 8 microns in thickness. And I think that's kind of thin to have a meaningful impact upon die life. However, we do know that reduced spray can significantly affect heat checking. And it's the PVD coating, the application of the PVD coating to the die that allowed a significant reduction in die spray. So here's some data on the right-hand side of this figure. This is data taken from research results from a university in America called Case Western Reserve University. They have what they call is a dunk tester. And the dunk tester takes in a steel sample and dunks it in a bath of molten aluminum for about 10 seconds, pulls it out, lets it cool, and then it's sprayed, and then it dunks again, and it goes through this cycle. It's kind of similar to a die casting cycle. And they, after 5,000 dunks and 10,000 dunks and 15,000 dunks, they take the sample out and look at the heat check-in and characterize the heat check-in in this way. And this is a machine or a laboratory technique that has been used in America for about 60 years and has really helped us develop information on die steels and heat treatment and process conditions on heat check-in. So what this figure shows on the y-axis is the amount of heat check-in. 600 is lots of heat check-in, 0 is obviously no heat check-in. And then on the bottom is spray time, and the three different lines are 5,000, 10,000, and 15,000 dunks. So if we look at the maximum spray time, 13 seconds, you can see after 15,000 dunks, we are seeing a lot of heat check-in. If we take that spray time down from 13 to 3 seconds, much less heat check-in. And if we go to no spray time, at least in the test they did at Case Western, they saw no heat check-in at all. Not to say that we wouldn't in a real die, but that's what they saw. So clearly reducing spraying allows us to minimize heat check-in. And so I personally think that the use of the PVD coating allowed us to reduce spraying, allowed us to get an increase in die life. But that's not yet been proven. That's just kind of my opinion at the moment. What the caster has done is looked at the cost benefit of PVD coating an entire die. They performed a cost comparison comparing manufacturing costs associated with the older uncoated die and the new PVD coated die, PVD coated with this aluminum chromium nitride coating. The cost comparison was actually performed last year in 2019 after about 70,000 shots had been produced in the PVD coated die. And here's some of their findings. So I talked about this a little bit earlier in the presentation, that the old uncoated die required 3 significant maintenance operations in terms of solder removal and then re-welding small pieces in critical areas. That was, they had 3 significant maintenance operations by the time they got to 70,000 shots. With the PVD coated die at 70,000 shots, maintenance has not been required. The first maintenance was actually required at 75,000 shots. Clearly reducing the amount of spray you use reduces cost because you can purchase less lubricant, and lubricant is not inexpensive. Reducing the cycle, improving the cycle time means that more castings are produced. Obviously that affects costs. But probably the biggest one is that the PVD coating, the reduced spray, appears to offset heat check-in, and therefore will get a significant increase in die life. So they actually, the caster actually did a quantitative comparison and looked at these 4 or 5 different parameters. And they looked at the savings after 70,000 shots as a percentage of the original tool cost. And so reducing die repairs, they said that represents a saving of 10% of the original tool cost. Reduced die lubricant, a saving of 5% of the original tool cost. Faster cycle, 5% saving of the original tool cost. And extending die life is a big one. Obviously, that's a huge one in terms of cost savings. And so they estimated that. We don't really know the final figure yet because the die's still running, but they estimated that it would be a 25% saving compared to the original tool cost. Now, from all that, you obviously have to subtract the cost of the coating. Doing these PVD coatings, again, is not inexpensive. And they estimated the cost was 20% of the overall cost of the original tool. However, total savings, 25%. That is quite an impressive total savings. So in terms of the plant trial status, the plant trial will continue with the PVD coated die. The plan is to run it to the end of life, so it might take us another couple of years or so to get there. And obviously, we want to determine how many more castings a coated die can produce compared to the old and coated version of 97,000 shots. So, in summary, it appears that there are many benefits of applying PVD coatings to die casting dies, not just in terms of small cores or small inserts, but larger portions of the die, or maybe, as we did here, the entire die. Firstly, a reduction in soldering and erosion problems. We know that. That's been known for a long time that PVD coatings provide those kind of benefits. But apparently you can get an improved cycle time as less time is required to spray the die. Cost can also be reduced. You're purchasing smaller amounts of lubricants, and expensive die repairs can be postponed to higher shot counts. And then most significant, I think, is that a significant extension of die life can be attained as we get reduced heat checking observed with the PVD coated die due to the reduction in the lubricant spraying times. So that's my presentation. I have, I think, finished just about on time. And so we'll be happy to take any questions if there are any.
I believe Tej has a question. Maybe you can put him on.
Go ahead, Tej.
Yeah, good evening, Steve. Thank you very much for a very enlightening session on the PVD coating. So one question with three sub-questions. You mentioned aluminum chromium nitrile coating. So can we not use, aluminum titanium or molybdenum as a substitute for this? And would they really help for a better die life or a better coating, surface coating? Question one.
We don't have data, but I suspect they probably would. So you're talking about aluminum titanium nitride, and then the molybdenum one I'm less familiar with. But we chose aluminum chromium nitride for several reasons for the tests that we did in America. During the laboratory test, there were three coatings that looked quite good. Aluminum titanium nitride was one of them. But we picked aluminum chromium nitride because I think it has better high temperature stability. So I think other PVD coatings will probably work. Whether they will work as well, maybe they will work better, I don't know. We have no data at the moment to compare them to. But I think in general, PVD coatings prevent soldering, prevent erosion, and therefore can reduce the amount of spray and get the kind of benefits that we were seeing in this study.
Okay, you think it would be worthwhile to go in for a trial with the titanium?
I think it would be. Yeah, the aluminum titanium nitride. Yes, I think it would be. I think it would be interesting to try that. And that seems to me, from my previous visits to India, that seems to be the most commonly used PVD coating in India. And I remember when I was training, I would ask people, and pretty much lots of people were using it.
Correct. So second question is that, have you drawn a comparison between the nitriding, the plasma nitriding and the PVD coating for, purpose of understanding the behavior and the difference in the die life and the coating, surface coating?
Yeah, so when you talk to die casters are convinced that nitriding will extend die life. And I cannot find any good evidence of that. And I'm actually beginning to wonder if it's a similar thing to what I'm seeing in this study, that by nitriding your die, you spray it less because you're soldering less, and therefore you get extension that way. But you talk to die casters, I've asked questions in classes, and die casters are convinced that nitriding, ferritic nitrocarburizing, will extend die life with heat checking. When people have done laboratory studies, they've not shown that. So nitriding is good for solder resistance, erosion resistance, but I think PVD coatings are better. There are some studies that were done maybe 10 years ago in America that seems to show that PVD coatings are better than just nitriding the dye. And was that your question? I can't remember exactly what the question was now.
Yeah, so yeah, that's right. And the last one is that, what are the challenges that you see in terms of handling the PVD coating dyes? Because we have this tendency of polishing the dyes and removing the soldering and the catching, etc. So, and you said it's 2 to 8 microns. So how do you handle that?
Well, that's a training issue, I think, is that people have to be trained to not just go in there and start, being very aggressive with the dye, because they will remove the coatings, and so people have to be trained that be more gentle with the dye. And it should be easy to use anyway, because soldering should be reduced and erosion should be reduced. But you do have to be a bit more careful not to reduce, because as I said, they are pretty thin, and you will go in and remove them if you're not careful.
All right, thanks very much, Steve.
You're welcome. Nice
Steve,
to talk to you.
There's another question from Mr. Janakara Balaji. He is asked that what is the expected life of the PVD coating, as you suggested?
Well, that's a good question. And again, we don't really have data on that. The caster that was doing this trial, we've talked to some of their engineers over there, and we're kind of asking them, how long do these coatings last? And they say as long as they die. And certainly, the fact that we are still being able to produce castings at a low lubrication level suggests that the coating is still in place in this dye. But we have not done a rigid test to kind of see exactly how long coatings last. So I don't have good data on that, but they do seem to be lasting quite a long time.
Okay. From Mr. Karthik Raja, he is asked, any H13 material can be done PVD coating, and any process parameter have influence on the coating life?
Well, let's take the first one. Yeah, I mean, you can coat any, there's H13 and there's new varieties of H13 out there now. Some of these new dye steels that the steel companies have come up with, and coating the various steels is not a problem. It does appear better to nitride the steel before you put the coating on. Because that provides a hard, stable layer underneath the coating to help stabilize it and to make sure that it doesn't deform. Because the coatings are not, the coatings are relatively brittle. And so if you kind of deform the dye, then they can crack off and stuff. And so people normally do plasma ion nitriding and then put the coatings on. Is kind of the normal way to do it. But you can put them on any kind of steel. And I forgot what the second half of the question was.
It's that any process parameter has influence on the coating life.
Well, certainly, if you blast, if you have a core in front of a gate and you blast your metal on that, your coating is not going to last as long as if you don't do that. But I don't know that there's any people kind of process parameters in terms of intensification or injection speed or things like that, liquid aluminum temperature that people have shown that help coatings last longer. Certainly, in general, being gentle with them is better. But I can't think of anything specific in terms of helping them to last longer. Normally, we pick coatings that have oxidation temperatures well above the molten aluminum temperature, so they're not going to oxidize away and things like that. And I think the two coatings we talked about here, aluminum chromium nitride and titanium aluminum nitride, both have oxidation temperatures well above that of liquid aluminum.
Okay. We have 3-4 more questions. I think, Steve, you'll have to answer them on the chat or maybe later on. because we are moving on to the next session. Anyway, this one was a very fine session that we had on the coatings from Stephen Midson. He's talked about the PVD hard coatings, which has resulted in the reduction in the amount of the lubricant and the heat checking marks, and also extending the life. He has given a very good study backed up with data, and I believe we definitely will have something to learn from it and maybe put it into the actual practice. Well, now I'll thanks Steve Midson. Thank you very much. It was a good session. Now I'll move on to the next speaker. Now the next program would be on the total thermal vision, temperature monitoring of dyes for light alloy casting. And this is by Mr. Adarsh Maheshwari, Senior Engineer, Business Development, Marposs India Private Limited. Now, Mr. Maheshwari has completed his Bachelor of Technology in Mechanical Engineering from UP Technical University, Lucknow. Currently, it is known as APJ Abdul Kalam Technical University. He is associated with Marposs Group from 2015 and was initially a part of product management team for grinding gauging solutions. Currently, he is having responsibility to explore and establish new business in Pan-India for new product segment of Marposs, that is total thermal vision solution for your PDC facility. He started his professional career with Tosei Engineering Private Limited in 2012 as a sales engineer, responsible for market development of shop floor metrological solutions for automobile industry. So welcome aboard, Mr. Adarsh Maheshwari. You can begin your session. You'll have precisely 35 minutes to go on, and then we'll have 5-minute question answer session after that. Over to you, Mr. Adarsh.
Yeah, thank you so much, Mr. Luthra, to introduce a little introduction of mine. Okay, yeah, very good morning to all. I hope all are doing well. And my name is Adarsh Maheshwari. I am representing the Marposs India. And today's topic for this session is to introduce our real-time temperature monitoring solution for the die surface. Okay, let me share my screen to introduce in a detail and to give you a detailed description of the total thermal vision, basically a real eye for your pressure die casting machines. Is it visible to everyone?
Yes.
Okay. Now let's begin. Welcome to all. Okay. Now, yeah. So basically, this is our today's approach. What I want to introduce, and for this session, the 40-minute session, we will discuss on this for the TTV approach and its applications, and the focus on drivers, and basically in a detail the system, its hardware architecture, and the software interface. Okay. We are moving ahead. This is kind of the approach which we will focus. It's a TTV approach. So TTV approach, what we will do with the TTV in the pressure die casting facility, we see and record the actual condition with the thermal vision. See and record the actual condition. That means we are seeing the what exactly the behavior, die surface behavior, temperature behavior on the machine, and we are capturing that behavior in a real-time conditions and storing it with the data in our hardware architecture. After that, through this data, when we recorded it, we used to analyze this data to optimize your die casting cycle. And after this, the target achievable and expected, what exactly your optimization, what you want to achieve with your die casting cycle, that's we can compared with your desired expectations. And when we will have the real condition, so we do have the parameters, we do have the aspects on which we need to implement our different optimization aspects to optimize all over your die cycle process. So here in the images, easily you can see this is a particular the live session, this is a recording session, and this is the analysis session. So there is a basically a very simple 3 steps for TTV when we will incorporate in our die casting machine. So these are 3 steps we will do it. So I'm just now want to play a 1.5-minute video, what exactly the application of the Marposs total thermal vision. So it will give you a clear indication for this process.
I think you have to share visible.
Unable to see it a while ago.
Hello?
Yeah, we were unable to see your screen. Now we can.
Okay, so that the video will be available to see you or not?
No, you will have to run it from your end. Would you need some help?
Okay, let me check. Most probably, one sec. Okay, now it is it visible?
Yes, now it's visible.
Okay, yeah, sorry for that. It's a 2-minute video which will give you the clear indication of the Marposs TTV application. Just have a look, and after that we will have a discussion. We will just
Sure.
give you the detailed description.
Go ahead. We are unable to get the audio, or have you muted that? It's coming interim. The audio is coming interim.
So basically, this video will showed you the real application of pressure die casting, the application of the TTV in a pressure die casting, and what exactly will the the behavior of our TTV system. Okay, now we will discuss further on this approach, on the TTV approach, and a detailed systems hardware and software architecture, and how we will can incorporate this kind of system in a pressure die casting machine. Okay, so basically now we'll talk about the TTV focus. Okay, so the TTV main focus when the approach for the TTV, and the focus is to reduce the cost of the cost of the production. Okay, and after that, for the optimize the cycle time and an increase in the die lifespan, increase machine efficiency, better analysis of process failure, minor uncontrolled process stops, process identification, and a part history. Basically, this is the focus with application of our real-time temperature monitoring solution. The cost saving in terms of the cost saving to reduce the lubrications, okay, in the machine, optimize cycle time when we have a real picture of your die surface temperature. So that means that the cycle time will be reduced because the uninterrupted session which used to going to happen in the cycle can be eliminated. Increase die life cycle span because like the preheating and overheating that can be reduced. When this phenomenon will reduce, that directly will benefit in increasing the die lifespan. And after that, when this kind of approach, this kind of things we can achieve in our machine, definitely it will directly increase the machine efficiency and the better analysis of the process failure when we have all the records of your real-time process monitoring. So it will definitely give you the analysis for a process failure, when is the process, like what exactly the points for the process failure. And apart from this, like the minor uncontrolled process stops and process identification and the part. Okay. Now, like the typical applications where we can utilize our TTV systems. So basically the TTV system initially originated for the high pressure die casting. Okay, after that, seeing its usefulness in the other die casting processes. So this TTV system is also being introduced in low pressure die casting process and a gravity die casting process. Okay, so this is the application, TTV application. So where the TTV can be useful, like you can see here the schematic view of a high pressure die casting machine. Okay, so here we install the two numbers of the cameras, including the controller systems, one for the fixed die and one for the movable die. So it's a standard applications, but apart from the complicated dies, we can also introduce the maximum 4 cameras on a single high pressure die casting machine to capturing the real-time images like before the spring cycle and after the spring cycle. So basically this is a schematic view to how to install, like where the cameras will be installed. And apart from this, now we are going for like the low pressure die casting. The low pressure die casting, what exactly we will do, we acquire the one image per each shot. In high pressure die casting, we are acquiring the 4 images per shots. And the same thing we can do with the gravity die casting machines, like according to the applications, according to the requirement of the dies, the complication of the dies, like the 1 or 2 infrared cameras, and we used to do the one acquisition per each shot. Okay, so we will talk about the focus on the drivers. Okay, the focus on the drivers, the initially, the simply means like what exactly the driving factors that will you need to think about this kind of system in your facility. First, definitely is the live monitoring of the process. This type of system will help you to give a live monitoring approach of your process. The usually the tradition of this approach, when the some operator will go to the machine, will have the pointed gun and all that to give to acquire the images from the die, and after that they go to the room and just see on the some computer and all that, and just after they used to like do some remedies or take some action. But in this session, when you have the live monitoring, you can see the live monitoring what exactly happening on the machine, and accordingly in the real time you can also take the actions. Okay. And second approach, second focus for the TTV systems, like the record from in process and offline analysis. First is the live monitoring. This live monitoring is used to record our system uh, to have a focus during the in process, and also to have a focus during the offline analysis. Like from the 1 week before, you have some pictures, you want to do some focus, you want to do analysis, you just call that picture for a particular time, particular shift, and a particular part number. So accordingly, you can do also have that analysis. When we go to the next step, it is a report. So this is quietly helpful to the manufacturing facility for the pressure die casting to make the reports for the each part, each batch, each shift. What exactly the behavior of my die casting cycles during that period. The fourth one, which is quietly like for like we are talking about the industry 4.0. So this is the basically main factor, the integration and the communication with the DCM, like the die casting machine, sprayer and thermoregulator. This TTV systems is very easily can communicate with your machine, with your die casting machine, with your sprayer and thermoregulator, and give the feedback, take the feedback from the machine also, and also give the outputs to the machine. And the things which right now regarding the ROI, and when we talk about the cost, so fast payback due to the improvement and the optimization. Okay, so in a detail, like you can see here, the live monitoring. It is here is a picture. You can see it is a high pressure die casting process. We are taking as an example. Here, like you can see the 4 pictures, 1, 2, 3, 4. Like the TC1 is a camera 1, TC2 is a camera 2. We are taking 2 pictures, 1 or 2, one before the lubrication cycle and after the lubrication cycle. Okay, the same here with the fixed die and a movable die. So it will give you the real pictures, what exactly the behavior of my die surface before lubrication and after lubrication. So it is useful for you to easily identify the preheated or overheated areas, and where you have to put your more effort on the critical points. So it will give you the real picture. After that, the record for in-process and offline analysis. Okay, here, like in the picture, you can see it will give you the real trend, like from the whole over the week, whole over the day, whole over the 1 hour, what exactly the behavior of the critical point. Like the ROI one, this is the reason of interest. Reason of interest, like in a particular die surface, you have a 10 points, or the maximum 10 points we can do with our system. So this 20 or 10 points, you can have a real picture where, what exactly the behavior of this 10 critical points or the 20 critical points. Okay, this is for the record for the in-process and offline analysis. Like you can just call that record from your past manufacturing data and just compare the real time. So if there's some problem mistake in a machine, like there's some points where we are not able to achieve, we're not able to achieve the part quality at some areas. So you can just call the picture from the good parts and just have the analysis. Okay, so apart from this kind of reports you can generate to have the analysis in your facility for all over the period. And this is for the integration and the communication part. Like as we set the different region of interest and the critical points to acquire the data, like the minimum and maximum temperature limits accordingly. So that data can be fed to the machine, can be fed to your thermal regulator and the sprayer. So when this data can be fed, so it is very useful to synchronize your cycle and to just optimize the lubrication cycle also, where you need to do more spray, where you need to do the less spray. So this kind of integration and a communication, you can do it very easily with this TTV system. So this is the main part. Also, like how we can achieve like the result in terms of the cost. because like the warm-up cycle, if we are talking about the warm-up cycle, in the warm-up cycle we can easily have the idea like the how much the shots is going to be like the warm-up shots. So when we like it is a trend, like we need to give the 10 standard shot, the warm-up shot, and after that the 11 will be the okay one. So when you will have the real picture, so it could be possible that the 3 or the 4 shots is only the warm-up shot and the 5th shot is the okay. So that is the thing you can do it, and we already achieved during like our past experiences and installation in the industries, that is the warm-up shots is directly we can reduce with the help of the TTV. Okay, now we will talk about the architecture system. Since it is a camera is used to a inline solution, and the inline solution is used to be make so hardcore system so that it can bear the harsh environment of the pressure die casting. So you can see here it is a stainless steel casing of our camera, and it is like the protected with a germanium glass in a ear shuttered when they're used to operate during when this camera get the enable cycle from the machine. So when the picture used to capture, the shutter will open, camera capture the picture, and the shutter will close. It is a, and also to take care of the temperature in the machine. So this is the vertex system, the air cooling vertex system. So used to cool that camera in the pressure die casting facility. So everything has been taken care to sustain this kind of devices in a real time monitoring solutions. Okay, here you can see. And after that, when we are going to, because it is the real eye, now this is the showcasing of the showcasing device, the display device for that like the camera. So here you can see we are used to provide the industrial PC for the facilities. Depending upon the application and the configuration of the machine, the standy one and the overhang one we used to provide for the machine. And it is depends you want to place this kind of devices, this kind of display near the machine or some at some distance of the machine. Everything configuration is possible depending upon the infra. And here you can see like the 4 pictures where to evaluate. Like here is the 4 pictures. You can see this is the ROIs. This is the ROIs. So this is very easy to evaluate each and every pixel also. Okay, this is not a matter of the like the only the 20 points or the 10 points you can just see. By moving this cursor, you can also have the the temperature of each and every pixel of the die. So this is the live view image where to evaluate at a glance the distribution of the temperature on the mold surface. This is basically the optimize the view and the save the manual pictures. And this is basically the setup page. Setup page, if you are talking about like as we set up like the 10 different points. So 10 different points when we used to get the alarm, like this is the preheated one, the overheated one. So we used to set up the T minimum and the T maximum. T minimum, it depend upon your specification of the die and the part, what exactly it is. Okay, so you can set it whether it is 100 or whether it is 300. So you can just set it, and accordingly you can also get the alarms when this is going beyond the limit or when this is lower the limit. So this is the trend we already discussed. And this is for the comparing between the pictures to pictures, like the live picture and your record data. And this is the report, like you can get it for your each and every shots. And you have that analysis, and you can just share with your customers, with your whatever you want to use it, this kind of data. This is behave just like a passport. So it is a passport for your every part. For a passport, like if you are talking about the high pressure die casting, you have 4 images for each part. So it will like a passport for a good component. Okay, during the process, these are the points I just like the maintained a like ideal temperature, maintained a like the that the temperature limits during the process. And this is the alarms, like what we're talking about the T minimum, T maximum. You can get it, the alarms in a real-time alarms to your DCM machine. And process and system alarms, depending upon like it is a detailed infra alarms, whether it is during the malfunctioning, you can get it in the machine. And basically this is the point, like the easy to like the export the data, because every data is stored in our machine. This data can be exported and easily can be shared on your sharing platform, in your cloud management, in your like through the SCADA, through the different platform. You can have that data and can easily see from wherever you want. And basically now we are talking about, because there's a different part is running on the machine, depending upon the part program and recipes. So there's a facility to create different recipes. So currently we do have the facility to the 50 recipes, so 50 parts on a single machine, on a single system. You can just have that create that recipe, and whenever the part is coming, you can just call that recipe, and that our system will be able to behave for that part on the machine. So this is for the communication, as we discussed already. Okay, so basically this is our like the more than 130 TTV systems worldwide we have supplied, and we have a good tie-up with the OEMs and the end users. Here you can see this is the system. Our system is having the partnership with the OEMs, like different pressure die casting manufacturers. And here the four-wheeler manufacturers, where we do have a population, a very good population of our TTV systems. And here is the tier 1 and the big suppliers, where they are using our system for optimizing their die casting process. Okay, here is a small glance of the Marposs India. So we do have a headquarter in our Manesar office, and we do have like the 100 plus employees strengths to cater all over the automotive and aerospace industries. And we do have every sales and the service locations available each and every corner of the India, and we are covering pan India market. Okay, so from the sales and service support, we do have equipped with all over the gadgets and with all over the manpower. And thank you so much for giving your time for this presentation. Now we can move forward for the questionnaire session.
Yeah, I think Tej again has some questions. Maybe we can put him on.
Yeah, hello. Thank you, Mr. Adarsh, for the presentation. So my question is, how do you calibrate the accuracy of this camera? When I talk about the real-time data that I take from the die and the data from the camera, what is the level of inaccuracy that one can see, and how do you calibrate the camera, the accuracy of the camera over a period of time?
So basically, sir, we have different models available for the this infrared sensors. So basically, if you are talking about the accuracy of the camera, it is used to a plus minus 5 degree. This is the accuracy of the camera. And when we are talking about the calibration, comes with the facility of the calibration of these cameras. Okay. So with respect to the ideal conditions and with respect to the black eye, it is options available in our camera. So we can calibrate this camera. Our team is available that the devices to use to calibrate the camera and use to validate what exactly the error is coming during the process. So this is the function is available.
Thank you.
Okay, we have another question from Mr. Janakara Balaji. What will be the maximum distance it can focus, and what will be the maximum temperature it can sense?
Hello.
Could you get the question?
Yes, sir. Yes, sir. Yes, sir. Okay. What exactly the maximum distance and the maximum temperature it can get? Huh? Okay. Okay. So yeah. So basically, sir, there is a pixel views, especially available we can do the fixing during the distance between the camera and the die. Okay. So it is basically the standard we are recommending is a 2 meter. But when we are just as far as the distance, when we increasing the distance, the pixels, the quality of the image is going not good. The quality of the image is going to deteriorate. whenever the distance is far. Okay, so recommended distance is the 2 or 2.5 meters. So the maximum we are recommending 2.5 meter installing on the machine. But if the machine is allows to place the camera close, so it is very good because the picture quality will be very good.
And what about the maximum temperature?
Maximum temperature, the 700 degree we can capture. And according to we have also the different cameras configuration. So we can also go beyond this, but the standard currently we are giving 700 degree.
Okay. From Vijay Kumar Saxena, he has asked can we interlock the TTV device with machine parameter so that the machine will stop if temperature of die is beyond spec? I think you have talked already on this about the alarms.
Yes. We can do it. We can interlink. We can interlink the DCM with our TTV systems. Whenever you can just have the program like some of the critical points, whether the 1, 2, 3, we have a capacity of the 20 points. So whatever the point will be like beyond that limit, you will get the alarm, hardwired alarm, or through the Profinet, whatever will be the capability of the machine, and you can with that output.
Okay, Mr. Vishwas Kale wants to know that something about the calibration of such devices.
Yeah, calibration is available, sir. We can do it the calibration. Okay, we do have the facility and we have the smart gadgets to do the calibrate of these cameras. Okay, so it is like not like this. It is not an inbuilt function on that. We used to do with support of our technical team for the calibration.
He also wants to know that. Okay, he's sharing some other information. Okay, Mr. Niranjan Toroskar also has asked a similar question. Can the equipment be interlocked with machine cycle start?
Yes.
For the required temperature pattern of the die?
Yes, it can be interlocked.
Okay. Mr. Sanjeev Prabhakar wants to know if there is any such installation in India.
Because sir, this system is introduced from the Marposs, this kind of application developed late in the 2017. So from the India, we are along with the ALUCAST also, we are promoting this kind of instrument from the 2018 itself. And currently we do not have any installation in India. We actually, we started from the European, the region. Now this system, this kind of approach is now shifted from the Asian market also. In the China, there's a lot of installation going on. In the Thailand, now the time comes from the India to acquire this kind of technology. So currently, we do not have any installation in India.
Oh, you are planning to have someone, or are there somebody has approached you for this?
Yes, sir. Definitely, we have a lot of inquiries in our basket because of this COVID situation. The freezing of these inquiries got delayed. Definitely, if the situation will not come, one installation in this year we were planning, but it got shifted into year 2021.
Mr. Maheshwari.
People also wanting to know something about the cost, but maybe you can.
Yeah, we can discuss personal to personal regarding the cost.
Yes, you can maybe answer it on the chat personally.
Yeah, Mr. Luthra, I would ask one question to Mr. Maheshwari.
Yeah, please.
Question. Mr. Maheshwari, we have installed these cameras on the machine that there is a safe picture of the thermal picture of both the dies after spraying is stored in the machine memory, and every cycle before that the image from the camera is compared with the cycle stored image on the in the memory, and then if it is not matching with that, with certain deviation allowed, the machine stops, it doesn't start. It always ensures that after the spraying, the machine having the thermocooling arrangement and the water cooling, it's perfect, and then only the machine will start. So can we have this type of system incorporated with the interlock with the machine?
Yes, sir. Yes, sir. Basically, the main funda of this kind of instrument, it is not comparing with any previous record. Okay, it is comparing the data with your set limits. Okay, like for the different points, we have set the limit like that this point cannot be go lower than the 100° and cannot be upper from the 120°. Okay, so these are the limits. My system is like behaving according to these limits. Okay, not from the past records. So it
I'm
is
not talking the past record. In the machine memory, the perfect image of the both the dies before the start of cycle is stored.
yes,
And every cycle, the image coming, real-time image coming from your camera is compared, and with some deviation is always given, a plus minus something. If it is not matching, the machine will not start. You get an alarm and you have to check. Sometimes the thermocooling liquid is not proper or the water cooling pressure is not proper. Then only machine starts, because this system I introduced in Chennai in Nissan Foundry, these cameras, and it works perfectly. The rejection is 0.001% of the casting. Yes, I'm asking you, can it be done interlock every
yes,
cycle?
yes, we can do it. We can do it.
Okay.
Interlocking, we can do it.
Yeah. Thank you.
Okay, one more question from Mr. Sandeep Kumar. He's asked that is there any special support software required with the camera to study thermal analysis?
No, no, there is no any standard like the special software required. We used to provide our own like the output devices to like capture these images in our own system. That's the thing. From our system, we can communicate to your machine or to your hardware very easily. But initially, the first channel is ours.
So that means it comes as a complete unit that gets attached to the machine.
Yes, correct, sir. Correct.
Okay. Maybe there are some few questions I might have missed in the chat. Maybe you can answer them one by one. Just go through that and maybe answer it. And I'm thankful to you for this wonderful presentation that you have made on the total thermal vision with a series of the live record analysis that you have talked and the three-step TTV approach. And then you have also gone on to show how it can be used in the HPDC, LPDC, and GDC applications. And the benefits that we do get in the form of reduction in warm-up shots. And we can also be setting the temperature limits in order to get the alarms, and we can do the correction on the machines accordingly. And you had also answered some questions on the optimum distance and maximum temperature and interlocking. We definitely look forward to this coming into our country and people maybe utilizing this. So thank you, Adarsh, for the very good session that we had. And I now hand over the mic back to Sameda for some hot tea that she's arranged for all of us, maybe virtually. Okay.
Mr. Luthra.
Over to you, Sameda.
Thank you so much, sir. Thank you.
So I think now it's time for a tea break. So we would have 15 minutes tea break starting now, and we resume back at 12:05. So see you all at 12:05 and enjoy your tea. Unfortunately, we can't serve you this time.
Okay, thank you.